So what if we launch a weather balloon and allow it to reach 10,000 meters? What happens to the volume? We know that as the pressure decreases, the volume increases. But as that balloon ascends through the atmosphere, the temperature decreases. So how would we determine the final volume of the balloon when we're changing three variables: pressure, volume, and temperature, while keeping N, or the number of moles, constant? Taken individually, none of the gas laws we've discussed fit this situation. So we are going to go through the derivation of the ideal gas law. We started with Boyle's law, which is relationship between volume and pressure. And I'm going to rewrite those relationships in the context of volume. And for Boyle's law, N and T are constant. For Charles' law, there's a direct relationship between volume and temperature, where N and P are constant. And for Avogadro's law, the relationship is between volume and number of moles, where P and T are constant. So we can add these together and we get V is proportional to N T over P. So that means that V is equal to some constant times NT over P, or rewritten as the ideal gas law, PV equals nRT, where R equals the universal gas constant, which is 0.0821 liter atmospheres over mole K. So the ideal gas law expresses all the possible relationships between four variables. And that's what makes it so useful. So an ideal gas is a hypothetical gas whose pressure, volume, and temperature behavior can be accounted for by this gas law. Or by the ideal gas law. And all of our gases at normal temperatures and pressures behave ideally. So we're going to work back through some examples for each of the individual laws. We'll start working with the ideal gas law. but recall that Boyle's law is P1V1 equals P2V2, and this assumes that N and T are constant. So the first question is, a balloon is partially inflated with 5 liters of helium at sea level, where the pressure is 1 atmosphere. The balloon rises to an altitude of 1,600 meters, where the pressure is 0.830 atmospheres. What happens to the volume of the balloon as it rises? And if you think about these relationships as you're working problems, you can catch errors in your setups or calculations. So what happens when pressure decreases? What happens to volume? Volume increases. So we should, when we calculate the volume at the higher altitude, get a volume that is larger than 5 liters. So an important part of working the gas law problems using the individual gas laws, Boyle's, Charles, Avogadro, is identifying what you're given and rearranging that equation appropriately. So we're going to be solving for V2. So we have an initial set of conditions and a final set of conditions. So we need to rearrange this equation to solve for V2. So V2 equals P1V1 over P2. So our initial pressure is 1 atmosphere. Our initial volume is 5.00 liters, and our final pressure is 0.830 atmospheres. So our atmospheres will cancel. We're left with a volume unit of liters, and the volume at 0.830 atmospheres is 6.0 liters. So our volume did increase as predicted. Second example, we have a scuba diver releasing a balloon containing 153 liters of helium from some underwater site. When the balloon reaches the surface, the volume is 352 liters. It doubled at the, or more approximately doubled. At the surface, the pressure is 1 atmosphere. What was the pressure at the underwater site? So we know, because the volume increased, that the pressure decreased. So we would expect a pressure at the underwater site to be greater than the 1 atmosphere at the surface. So in this example of using Boyle's law, we are looking for P1. So P1 equals P2V2 divided by V1. So we're just plugging our data in here. P2 is 352 liters. I'm sorry, that's V2. P2 is, I mix these up, 1 atmosphere. P1 is what we're looking for, and V1 is 153 liters. So liters cancel, and we'll get our pressure units in atmospheres, and at the underwater location, the pressure is 2.30 atmospheres. So we did get a pressure greater than the 1 atmosphere at the surface. So now we're going to look at Charles' law individually, and this is the relationship between volume, and temperature, and V1 over T1 equals V2 over T2. And here, P and N are constant. And temperature is in Kelvin. So remember, anytime we have temperature in a calculation for gas laws, that temperature must be in Kelvin. So in this example, we are determining what temperature is required to increase the volume of a sealed balloon from 2 liters to 3 liters if the initial temperature is 15 degrees Celsius. So we have temperature, as I said, so we need to convert our degrees Celsius to Kelvin, and that conversion is degrees Celsius plus 273.15. So K here is 15.0 degrees Celsius plus 73.15. K equals, 288.2 Kelvin. Notice we have 1 decimal place. We're adding. The sig fig rules for adding is least number of decimal places. So we have only 1 decimal place here for our calculation. We are solving for T2. So we need to rearrange this equation. So T2 equals V2 T1 divided by V1. V2 is 3 liters. T1 is 288.2 K. And V1 was 2 liters. And that gives us a temperature to 3 significant figures of 432 Kelvin. So notice that to increase the volume by 1.5, which is what we've done, the temperature in Kelvin must also increase by 1.5. And as expected, because volume is directly proportional to temperature in Kelvin, but not in degrees Celsius. Second example here, we have a 2.68 liter sample of gas. We are heating it from 250 K to a final temperature of 398 K. Again, assuming P and N are constant, what's the final volume? So now we're solving for V2. So we have V1 over T1 equals V2 over T2, and we rearrange that. So V2 equals V1 T2 over T1. And just plug in our variables then. V1 is 2.68 liters. T2, we are given this in Kelvin already, 398.0 K divided by T1, 250 K. K's cancel, or Kelvins cancel, and our final volume is 4.27 liters. And once again, thinking about the relationship between volume and temperature, we would expect that volume to increase as temperature increases. Now we're going to do an example problem for the ideal gas law, and then we're going to derive the combined or general gas law equation. So we have a bottle that contains 5.9 liters of O2. It has a pressure of 138 atmospheres at 25 degrees Celsius, and we want to know how many moles of molecular oxygen are present in that bottle. And this requires PV equals nRT. This is the only equation we have that we could utilize given the information we have to solve for moles. So we're given pressure, we're given volume, we're given temperature. R is a constant. Remember, R equals 0.0821 liter atmospheres mole K. So we need to rearrange PV equals nRT to solve for N. We also need to convert our degrees Celsius to Kelvin. One decimal place, so 298.2 K. So N equals pressure in atmospheres. Watch your units. If we'd been given something like millimeters of mercury or torr, we would have had to convert those to atmospheres. 5.90 liters. Our universal gas constant, which will allow us to cancel all the other units except for moles. So we can cancel liters, atmospheres, kelvins. We're left with moles. And to three significant figures, we have 33.3 moles of O2. So, what if our weather balloon is filled with 100 liters of helium, launched from sea level, where we have temperature and pressure, and allowed to ascend to 10 kilometers, where we have a temperature and pressure that is different. No gas is added or removed, so N is constant. How can we calculate the volume of the balloon at 10 kilometers? We're going to do that by using the combined gas law. And P1V1 equals N R and T1. N and R are constant. And we can say that P2V2 equals N R T2. If we rearrange both of these equations to equal R, we get P1V1 over N T1 equals R, R, and P2V2 over N T2 also equals R. Because both of these relationships are equal to R, we can set them equal to one another. And here, in this case, N is constant, so I'm going to drop that out of my equation. Okay, so this is the combined gas law. We could include N, but as I just said, N is constant, so we can cancel that out. So let's solve this problem. We want to solve for V2. So we need to rearrange this equation. So V2 equals P1 V1 T2 divided by P2 T1. There we go. So now it's a matter of plugging this in. Please note that our pressures are given in torr. And remember that 1 atmosphere equals 760 millimeters of mercury equals 760 torr. Because we don't use R in this equation, we do not need to convert torr or millimeters of mercury, if we were given that, to atmospheres. So we can just move ahead with the torr unit. However, we do have to convert our temperatures to Kelvin. So T1 equals 20 plus 273.15, and T2 equals negative 52, no, that's a negative, plus 273.15. So we get, and I'm, let's see, here we go, 293.2 and 221.2 Kelvin. So we have 755 torr times our initial volume, which is 100 liters, T2, 221.2 K, and this is divided by P2, which is 195.0 torr. See, our torrs will cancel, and 293.2 K. So torrs cancel, kelvins cancel, we're left with liters, our volume unit, and V2, or the final volume, is 292 liters. 3 sig figs due to our, whoops, I'm sorry, there should have been a 0 there. 0.0, 4 sig figs. Okay, so now we're going to include some stoichiometry with the ideal gas law. Remember, I told you some time ago, stoichiometry is not going away. We use this all the time. So, here's the question. How many grams of sodium chlorate are needed to produce 125.0 liters of molecular oxygen, or O2, when the pressure is 1 atmosphere and the temperature is 20 degrees Celsius? We are told that sodium chlorate reacts with solid Fe, iron, to produce molecular oxygen, sodium chloride, and iron 2 oxide. The other thing I told you was naming wouldn't go away, nor would writing a balanced chemical equation. So that is involved also in this problem. So we need a balanced equation. Sodium chlorate has a formula of NaClO3, and that reacts with Fe, iron, and these are both solids, by the way, and we produce molecular oxygen in the gaseous state, sodium chloride, solid, and iron 2 oxide. So if we have iron 2 oxide, that means we have Fe2 plus reacting with 2 minus. So we have FeO. This 2 will be a solid. Is this balanced? It is. So we don't have to do anything further. So how do we approach this problem? Ultimately, we want to know the number of grams of sodium chlorate that were needed or are needed to produce 125 liters of O2. Okay, so 125.0 liters of O2 from our reaction. So in order to use stoichiometry, we need to know how many moles of O2 are in that 125 liters. And we can calculate that using PV equals nRT and solving for N, number of moles. So N equals PV divided by RT. So we do have one conversion to do, and that's converting degrees Celsius to Kelvin. Whoops. So we have K equals 20 degrees Celsius plus 273.15. So we have 293.2 K. So number of moles of O2 are pressure of, what was it, 1 atmosphere times volume, 125.0 liters, divided by the universal gas constant, times our temperature in Kelvin. Kelvins cancel, liters cancel, ATMs cancel, and we have 5.196 moles of O2. 3 sig figs here. I'm going to go ahead and round that to 5.20 moles. So now we apply the stoichiometry. So the first step in our solution was determining number of moles, and now we're going to go from moles of O2 to grams of sodium chlorate. So we have 5.20 moles O2, and the stoichiometry from the balance equation tells me 1 mole of O2 is equivalent to 1 mole of sodium chlorate. Now I need the molar mass of sodium chlorate to convert to moles, or grams of sodium chlorate. 106.44 grams. So moles O2 cancel, moles of sodium chlorate cancel, and the grams of sodium chlorate required to produce 125 liters of molecular oxygen to 3 significant figures is 553 grams of NaClO3. So now we're going to introduce one more gas law, and it's called Dalton's law of partial pressures. And in this relationship, we are going to look at the pressures of gases that are in a mixture. So for any gaseous mixture in a container, the total pressure is equal to the sum of the partial pressures of the component gases. And the partial pressure is the pressure the component gas would have if it alone occupied the container. So we have two gases, P1, or gas 1, gas 2. Gas 1 has a pressure of P1, gas 2 has a pressure of P2. And when they're combined in the same container, when B and T are constant, then the total pressure is going to be the sum of the pressures of the two component gases. So there's another way to indicate or quantize the amount of gas in a mixture. And this is the only place we're going to look at this, and probably won't use it this semester, but if you go on to 1062, you certainly will. And that is something called the mole fraction. And we're going to consider two gases, A and B, in a container of a fixed volume. Okay. So individually, we can calculate the pressure of gas A using PV equals nRT and the number of moles of gas A. And we can calculate the pressure of gas B using the number of moles of B. And if you look at the mixture here, the moles of each gas do not appear to be equal. So one will have a higher pressure than the other because there's more of it. However, we can express that as a mole fraction. So how do we determine a mole fraction? We know that P total is going to be the sum of the partial pressures of the component gases, which is P of A, or PA, plus PB. And to calculate a mole fraction, we divide the number of moles of a component gas by the sum of the total number of moles present. So the mole fraction for A is the number of moles of A divided by the sum of the number of moles of A plus the number of moles of B. And likewise, the mole fraction of B will be the number of moles of B divided by the total number of moles. And this mole fraction, and I'll show you examples of these calculations, can be utilized to calculate the pressure of A and the pressure of B using these equations. So P of A will equal the mole fraction of A times P total, and P of B will equal the mole fraction of B times P total. So essentially, the partial pressure of a gas is going to be the product of the mole fraction times the total pressure. Okay. So this I just indicates any gas, whether it's A, B, so forth. And of course, the mole fraction of whatever we're focusing on is the number of moles of that component divided by the total number of moles. So the partial pressure of a gas is proportional to the quantity of the gas in a given volume and does not depend on the identity of the gas. So I'm going to do just a couple of examples and summarize this. So if we're asked to calculate P of O2, so that's the partial pressure of O2 in atmospheres, or ATMs, in the air outside of an airplane. And we are at an altitude of 33,000 feet. I think that's a fairly normal cruising altitude, where P equals 190.0 millimeters of mercury, and we are told that the mole fraction of O2 equals 0.209. Something I didn't indicate on the previous slide was that the sum of mole fractions in a mixture must equal 1. Okay? So using the equation from the previous slide, P of O2 then is going to equal the mole fraction of O2 times P total, which we are given. So this is 0.209 times 190 millimeters of mercury. We were asked to report this in atmospheres, so we are going to multiply that by 1 ATM over 760 millimeters of mercury. So P of O2 equals 0.0523 ATM. So just to summarize and give you one more example, the mole fraction then expresses the ratio of moles of a component gas to the total number of moles. And that's of gas in the mixture. There are no units. All units cancel. Moles cancel. So remember, there aren't too many quantitative descriptions in chemistry that don't have units, but this is one. These are mass-based because we use molar mass to get the number of moles. So it can be used for solids, liquids, and gases. And as I stated before, mole fractions of the components in a mixture total to 1. And I'm going to try to squeeze just one more problem in here, because I don't think I have another blank slide, but in case I do or don't, we'll have done this example, and if we do, we'll just skip over it. or introduce the next topic. So we have 100 moles of atmospheric gases. So that would be our total number of moles. And within that 100 moles, 21.9 moles are molecular oxygen, and 78.1 moles are molecular nitrogen. What are the mole fractions of O2 and N2 in the atmosphere? So we're just calculating mole fractions of O2 and N2. We're given the number of moles of each. We're given the total. So mole fraction of molecular oxygen is 0.219, and the mole fraction of N2 was 0.781. And if we add these together, they total 1.000. So they add up to 1 perfectly. So now we're going to discuss collecting a gas over water. And in many cases, the amount of gas that's evolved by a reaction is of interest. But since gases have such small densities, it isn't practical to collect the gas and find its mass. So for gases that aren't soluble in water, it's possible to collect the evolved gas by displacing water from the container. And that's the kind of setup you're looking at right now. And if you took 1020 at Normandale, you had a lab in which you collected carbon dioxide gas in a bottle after an Alka-Seltzer tablet reacted with HCl. So you have a bottle that's filled with water, and it's inverted in a tub of water. A hose connects a test tube that, this isn't the reaction 1020 does, but it is a reaction that produces oxygen gas. And so that oxygen gas is then displacing the water in the bottle. And then you can determine the volume of the gas collected. So during that reaction, the water level will adjust so that the pressure inside and outside the container are the same, which will be the pressure of the atmosphere. However, there is a significant amount of water vapor above the level of the water in the bottle. So we have to adjust for this vapor pressure from the water to get the correct pressure of the oxygen gas. So we're essentially collecting a wet gas. And to get the dry gas pressure, we have to eliminate that vapor pressure. So this is the reaction that occurred, and the total pressure, so that's the atmospheric pressure, is going to equal the sum of the pressure of the O2 plus the partial pressure or the vapor pressure of water at that particular temperature. So we're going to run through an example of this type of problem. And in this example, we are actually looking at the reaction that was depicted in the prior slide. And we need a balanced equation. So I have expressed the reaction in words. You should be able to write one of these equations and balance it if need be. But this balanced equation is 2 KClO3, and this is a solid, to produce 2 KCl and 3 moles of molecular oxygen. We're told that the oxygen is collected over water at 22 degrees Celsius. We're given a total pressure of 752.0 millimeters of mercury, and the question is, how many grams of potassium chlorate are needed to prepare 2 liters of O2 gas? We are given the vapor pressure of water at that temperature. So we're given the temperature of the water, which is presumed also to be the temperature of the gas. So we need to use the ideal gas law in the first step of this problem. So we're going to use PV equals nRT. Keeping in mind, this is P of O2, V of O2, T of O2. So there are a couple of things we have to do here. We have to convert temperature to Kelvin, and we have to determine the pressure of O2. We already have the volume of O2, and we're solving for number of moles. So we can use stoichiometry from the balanced equation to determine the number of grams of potassium chlorate that are needed. So we rearrange this equation to solve for N. And let's see, P total equals P of O2 plus P of H2O. P of O2 then is found by subtracting the vapor pressure of water from P total. Our pressures are given in millimeters of mercury. Ultimately, we need those in atmospheres, but I'm going to start with millimeters of mercury, and total pressure is 752.0, and from that we subtract the vapor pressure of water. Oops, that's 20, sorry. 20.0, and these are millimeters of mercury. And then we'll convert those to atmospheres. And our temperature in Kelvin equals, 22 degrees, sorry. 22 plus 273.15 equals 295.2 K. So number of moles equals, I didn't finish this. This is 0.963 ATM. And our volume is 2.00 liters. And we'll divide that by the universal gas constant. Times our temperature in Kelvin. Kelvins cancel, atmospheres cancel, liters cancel, and number of moles of O2 equals 0.0795 moles O2. So our second step is then to use the stoichiometry from the balanced equation. So we'll go from moles of O2 to moles of, we're using potassium now. Oops. To grams. Stoichiometry from the balanced equation. 3 moles of O2 are equivalent to 2 moles of KClO3. Then we need the molar mass of KClO3. Moles O2 cancel, moles KClO3 cancel, and the number of grams of KClO3 to 3 sig figs required is 6.50 grams. Here's another example of this type of problem, only a little different. Aluminum carbide reacts with 12 moles of water to form 3 moles of methane and 4 moles of aluminum hydroxide. If the methane is collected over water at 25 degrees Celsius and the total pressure is 728 millimeters of mercury, what is the volume of methane produced from 54.7 grams of aluminum carbide? The vapor pressure of water at 25 degrees is 23.8 millimeters of mercury. So once again, we need that balanced equation. So we have Al4C3 plus 12 moles of water, giving us 4 moles of aluminum hydroxide and 3 moles of methane gas. So this actually is the reverse of the prior problem. We're given the mass of aluminum carbide and asked to find the volume of methane that's produced. So the first step in this calculation then will be using the stoichiometry to go from grams of aluminum carbide to moles of aluminum carbide to moles of methane. Then we can use PV equals nRT to calculate the volume of methane produced by that mass of aluminum carbide. So we have 54.7 grams of Al4C3. Use the molar mass to convert to moles. And that is 143.95 grams. Use the stoichiometry from the balanced equation. To convert to moles of methane. And to three significant figures, we have 1.14 moles of CH4 gas. So before we can use PV equals nRT, we need to determine the pressure of methane. So P of CH4 equals P total minus P of H2O, because this gas is collected over water. And we were given the total pressure of 728 millimeters of mercury, the vapor pressure of water at 25 degrees Celsius, and these are in millimeters of mercury. We need to convert those to atmospheres because we'll be using the universal gas constant. And this is 0.927 ATM. Third step, PV equals nRT, where we're solving for V. We calculated our number of moles in the first step. We have our constant. And, we need our temperature in Kelvin. So temperature equals 25 plus 273.15. So we have 298.2 K, which we divide by our atmospheres of 0.927. K's cancel, atmospheres cancel, moles cancel. We're left with liters, and our volume to 3 sig figs is 30.1 liters of methane. So now we're going to go back and take a look at densities of gases and how we can calculate those, and how we can use PV equals nRT to not only solve for densities but molar masses. And that will conclude this video. However, there will be one more where we discuss the kinetic molecular theory in addition to effusion and diffusion. So we know that density equals mass divided by volume, and densities of gases are given by grams per liter. So density of a gas at STP, standard temperature and pressure, can be calculated from its molar mass and molar volume. So this is one way we can calculate a density of a gas. So for example, carbon dioxide has a molar mass of 44.09 grams per mole. So density at STP is going to equal molar mass divided by molar volume. So that is 44.09 grams per mole divided by 22.4 liters per mole. Remember, the molar volume of any gas at STP is 22.4 liters per mole. So moles cancel, and the density then of CO2 at STP is 1.96 grams per liter. We can also calculate the density of an ideal gas for any combination of temperature and pressure using the ideal gas law equation. Because density is by definition mass divided by volume, we need to identify the terms in the ideal gas equation that represent density. So the mass of a sample can be determined from the number of moles of a sample, right? So mass of sample can be calculated by using number of moles and molar mass of whatever that substance is. And keep in mind, V in the ideal gas law represents volume. And density of a gas is mass per unit volume. So if we look at PV equals the nRT, N equals, or can be determined by the mass in grams divided by the molar mass. So we can actually substitute that into PV equals nRT. So PV equals mass in grams times RT divided by molar mass, which of course is grams per mole, so molar mass times P divided by RT equals mass in grams divided by volume, or density. So let's look at the units on the left side of this equation, where we have molar mass in grams per mole times P, which of course is in atmospheres, divided by liter atmosphere over mole K times K, which of course is temperature. So this is R and this is T, equals grams per liter density. So moles cancel, atmospheres cancel, kelvins cancel, and we're left with grams per liter. So let's do an example calculation. So we want to calculate the density of air at 1 atmosphere and 302 K. And we're going to assume that the air has an average molar mass of 28.8 grams per mole. So density equals molar mass times P divided by RT. We have 28.8 grams per mole times 1 atmosphere divided by the universal gas constant, and our temperature in Kelvin. So the density of air at 1 atmosphere and 302 K equals 1.16 grams per liter. Once again, I am not sure if I have another slide here, so yes, I do. Never mind, I do. So hang on, I'll finish up this discussion on this slide. And here we are going to calculate molar mass from density, or from the density of a gas. So we know that D equals density, molar mass, times pressure over RT. So we can rearrange this to say that molar mass equals D RT over P. So once again, or we could use PV equals nRT, where we know N equals mass divided by molar mass. And units here then are going to be grams over grams per mole. So PV equals grams RT divided by molar mass. And we can rearrange that now to solve for molar mass, GRT over PV. Notice we have grams per unit volume in liters. So we can rewrite this as D, the grams per V, RT over P. If you should need to use any of these equations or need any of these equations other than PV equals nRT or the individual gas laws, I will give them to you. So I mean that I would give you these equations, but you need to know the basic gas law equations. And one more video will be up and coming. So study your gas laws.